Hello, this is Arjang. So today I'm going to talk about the chapter 3. In chapter 3 we are used the deflection. We calculate the deflection for different beams using double integration method. In your book the comprehensive examples have been performed. However, it is really important that you have the opportunity and chance to know how to model these beams in STAAD Pro and then compare your hand calculation with the results generated from STAAD Pro. So let's start. So it's a new project. Let's make it plain. Let's make it structure. So chapter 3, example 8. Then we have to specify the directory. Let's make a directory for ourselves. So it's gonna be chapter. Let's call it chapter 3. Next, the unit is fine. Next, it is asking me a specified path doesn't exist. Do you want to create it? Yes, sure. Then I create this path. Then I'm gonna add beam and finish. Our beam is very simple. It's a simply supported beam with two concentrated moments at the ends. So I'm gonna close this grid, make it front view. Very simple procedure. Then my beam length is 20 feet. So my first node is 0. And then my second node is 20. Then the next step is going to be connecting these nodes together with a beam icon. Okay, after it is connected, the next step is that we have to define so it is a steel beam. The modulus of elasticity is 29,000 KSI and the moment of inertia is 1000 inch to the power of force. So in order to do that, we have to go to the general tab, properties. We have to define a section. Define. We have many options. You can opt to have a circle or rectangle that have the same moment of inertia, or you can go to general and define a IZ as a foot to the power of force. Do you see the unit doesn't match the material? Let's call it steel. However, the unit is foot. What should I do? I'm gonna close it. There is a unit system. I have to come here, change my graphical. There is another one, change input units. I'm gonna come here, change the input units, foot kilopound. I'm gonna make it inch. Okay, then I'm gonna define general section, moment of inertia 1000 IZ, because be careful, it's gonna be your moment around Z, so the bending moment. Then the material is steel, add, close. When it is steel, automatically your modulus of elasticity is gonna be 29,000. Then we are done. The only thing that we have to assign it, use cursor to assign. I assign this to our beam. Then the next step is we have to define the supports. I'm gonna come here, support, create. I have a pin, so I'm gonna add it. And I have a roller. I'm gonna come here, fixed spot, roller. Then I select these, then add. Then I'm going to assign the pin to the left hand side, and the roller to the right node. The next step is that we have to define the load. I'm going to come here, loads, load case details, add. I'm going to add this first load case, then close it, and under this load case I'm going to add two concentrated moments. The direction of these moments are counterclockwise, and so we have to put them positive in our system. So it's going to be nodal load MZ keep inch. The unit is keep inch. Be careful. Now we are gonna change the unit again. So I'm gonna come here. While when we are in load items, we cannot change it. So we are gonna go one step back in the support. I'm gonna go one step back, change it to the feet. Okay, then we can continue to the load case. Expand these load case details on the load case number 1. Edit. It is fine. Then we should add this load. Then we add that. Then the next item that we have to deal with is that we are going to put nodal load MZ. It's going to be, for the first M, it's going to be 12 keep feet. Add. And the next one is going to be M over 2. It means 6 keep feet. Correct? It is added. You want save. Save it. Then close. So we have two loads. The first concentrated moment is going to be applied to the first node. And the second one is going to be applied to the second. You see the scale is very big, so we have to change it. So I'm gonna come to scale, make it apply immediately. We have a point moment. I'm gonna increase it in order to make it smaller. Correct? Okay. If you want to see the values, right click, labels, then go to the load display options and load values. Okay, so we should see 12 and 6 on top of these moments, concentrated moments. The next step is that we have to run the program to see what's happening. Our goal is to find a slope and deflection at point A and B, which is point 1 and 2, and at the midspan point, and also determine the maximum deflection at its location. Okay, then we are going to define the analysis type, add, then close. Then I'm going to go analyze, run analysis, save. We have warnings because we only defined the one parameter for moment of inertia. Then if you look at the post-processing of the beam, you see the deflection. Let me see if it is the scale that it doesn't show. I increase the displacement. So it is the view of the beam deflected. If you want to see the values, it's going to be seen here. You can see the rotation at point A and B. If you want to change the display unit, we can come here, section unit, dimension, structure unit, make the displacement in inch, and make it 5 decimal. Displacement is in inch, make it 5. Okay, so you see the displacement growing. However, we need also the radian in the force unit, rotation, radian, and make it 5. Okay, so it can be seen that the rotation at the first node is 0.00298. We calculate, we come up with 0.003. So we are good, we are fine. And the next thing that we have to check is the displacement. So results, view values, beam results, displacement, maximum results, annotate, close. So the maximum displacement that we got is 0.0105 inch. It matches the hand calculation. It's the same. So if you wanna, these are the table of the results, and if you wanted to have a mid-span point, also I recommend you to make a note at the middle of your beam. And so for instance, you can take a picture of this one, make it maximum displacement, then also we have, the good point is that we have to also check the reactions to check they are correct. So these are my reactions. Then also for the shear force diagram and bending moment diagram, it's important, really important. So it is I'm gonna go to results, view values, make it ends, annotate, close. So I see that. So I'm going to take a picture of that also, bending moment diagram. And also, if you want to see the shear force diagram, I should enable this, enable Fy. And this is my shear force diagram. SFD. Then now I'm ready to generate a report. So I'm going to form report setup, make the pictures, bring all the pictures to the right. Then, okay, or print here. You can print it as a PDF. Okay, asking you where you want to save. Let's save it here. Now it is the report that is generated for you. Thank you so much. It's really important that you check your answers with the hand calculation, and the comprehensive hand calculation is offered to you in the Structural Theory 1 Examples book. Thank you so much. See you in the next one. Bye.